Hello, geometry students. I appreciate you finding time to get your notes taken care of. Today we're going to be looking at a topic we have discussed briefly over the last couple of weeks, and that is the idea of composite shapes. Since we're in a unit talking all about the area, of course we're going to be finding the areas of those composite shapes. Our objective for the day is the student will learn to adapt existing shapes and formulas to fit composite shapes. As always, press pause anytime you need more time to get your notes copied down, and then hit play when you're ready to move forward. Now, this is going to be the last of the information going towards the next test. This is not a long unit. Okay, so you're either going to have to be able to master these calculations or not. We're not going to spend a ton of time working on the same information over and over again, so please take the initiative, make sure you can work your problems, and be ready for the upcoming test. So let's take a look. Now, sometimes we are going to have to be able to find the areas of figures that are not shapes that we recognize. The trick is to make them into normal shapes that you can find the areas of. In fact, this has been kind of a recent favorite thing for test writers to do, as far as on an ACT or an SAT or a TAKS or a STAR or anything like that. Instead of just giving you flat out a triangle and saying, here, find the area, which in all honesty is a skill that every junior high student ought to be able to do. What they are doing is they are taking a triangle and adding a shape onto one of the sides, or perhaps even removing a piece of information away from the triangle, or away from the shape of the triangle, and then asking you to calculate the area of this new unknown shape that they have built. Okay, so let's take a look at what we're really talking about here. Okay, this would be a very simple composite shape. Okay, but let's say we were asked to find the area of it. Okay, now obviously there's no numerical information attached to this one or anything like that, so we're just speaking in general. Okay, but if we were going to calculate the area of this thing, well, the first thing that would come into mind is it's not a particular type of shape that we can define. Of course, we can say it's a hexagon. It is a six-sided polygon, but it's certainly not a regular six-sided polygon, so we don't have a formula to go along with this guy. So what we would do instead is we would figure out a way to redefine the shape. Okay. Now there's a couple of different theories, okay, or methods of thinking to go along with this. Okay. First, we could think of it in the idea or the mindset of two recognizable shapes that have been joined together. If that is the case, then we could say, hey, I see a rectangle, I see possibly a square, okay, or at least a smaller rectangle, and rectangles are shapes that we have formulas for. So instead of a concave hexagon up from above, we have two very simplistic rectangles that have simply been added together. So that's what we would do. We could find the area of each of our rectangles, and we could add them up. Now, another way of thinking about this would be like this. Okay, you may prefer to think of composite shapes as a larger shape that is missing a smaller one. So again, no need to copy this guy down again. You already have him. Okay, we've already said that we have no formula, so we would come up with an alternative definition for this concave hexagon. And as we said, another way of thinking about it is a larger square or rectangle, depending on the measurements of this thing, that is missing its top right corner. That a small square or small rectangle has been removed away from this corner. Well, if that's the case, once again, we have formulas to accompany a large square or rectangle and a small square or rectangle, and we certainly know how to do subtraction. So it's not a big adjustment to deal with this idea. Now, as you can imagine, composite shapes can get as simple or as complicated as the imagination of the person putting it together. Okay, but in most cases, it is simply a matter of coming up with a mental definition for what it is that you are seeing applying the formulas to that definition, and then doing the math. Okay, so let's actually take a look at this figure. Okay, here it is again, applied some information as well as some measurements. Press pause if you need a moment to copy it down. Now let's actually run this shape through the two different calculations that we just said. We could think of it as a rectangle on the left side and a square on the right side that have been joined together. Now, if that's the case, okay, we have kind of a pictorial or a diagram definition of the way that we're treating this problem. Now let's apply some formulas to go along with it. This long guy that is on the left side is definitely a rectangle. We've got all the right angles running around the interior angles of it. Okay, so this area is going to be base times height. And then when we look at the little guy that's on the right, it should be clear that it is a square. We can see the right angles, so it's trying to be a rectangle. And then we see the side links matching up on the sides, so it looks like we are going to have a square. Okay, now I would go ahead and transfer the information that you do know from the picture as far as side links. I would move those over to your new diagram. Okay, there's kind of the important information. And then we would plug in the values that we have. For our rectangle on the left, we have a base and a height. Well, of course, the base and height are simply perpendicular to each other, so that is very clearly the 4 and the 2. To that, we are going to add the little square over on the right side. He has a side length of 2. Okay. Now remember your order of operations. Multiplication must be done before addition. Exponents must be done before addition. And lastly, and please excuse my dear Aunt Sally, we have our addition. Okay, so by the idea of adding up two smaller shapes, we have a final answer of 12 square units. Okay, now let's look at it the other direction just to prove the point. Let's assume it was a larger square that had a smaller square taken away from it in the upper right corner. Okay. Once again, I'm going to transfer the kind of the important information over to a new diagram. I don't know why I put a 3 there. It's a 2. Okay. And I'm going to write a formula to go along with this guy. Now, the overall shape that we've got traveling around the perimeter of this item, or this composite shape, is a square. We can see that we have right angles in the interior corners, and we have side links that are congruent. Okay, so it is a square. From that, we are going to remove another square. Again, the right angles for the little square in the upper right, and we have side links that are matching, so it's equiangular and equilateral. We have a square minus a square. Okay, so simply plugging in our information, we have a side length of 4 on the big square, side length of 2 on the little square, 16 minus 4, and once again, we have 12 square units. So as you can see, you're going to end up with the same result either way, as long as you're able to interpret the picture correctly and get the correct values and plug them in. Now, it's not always going to be, you won't always have this many options as far as how to proceed with a composite shape, because as you will see, some shapes lend themselves towards thinking of them like we did on the left, as two shapes being added together, where other shapes that we're going to see lend themselves towards being a shape that is missing another shape. Okay, so let's take a look at another. Okay. Here is some type of a quadrilateral. In fact, I would believe that would be the best thing that we could call this is a quadrilateral. It does not seem to possess any properties of any of the special quadrilaterals that we have seen, such as side lengths being parallel to each other, side lengths of being congruent to each other, interior angles being congruent. Okay, this is simply a quadrilateral. But if we're asked to find the area of it, we have no choice but to continue going forward. Okay. Now, there are options. Okay. We could think of it as perhaps a large shape, like this square that I just drew in, that is missing this right triangle and this right triangle and this right triangle. And if we do that, square minus triangle minus triangle minus triangle, we will most likely get to the answer. Okay. However, that is going to be several formulas, so we might want to think about it as an alternative way. Maybe we can look at two or more shapes that are being added together. Okay. Now, one of the things that I see is right across here. Okay. If we look at it like that, it is possible we could treat this as a right triangle right there in the bottom half, and then we could drop in an altitude right there and look at it as two triangles being added together. Now, I think I would opt for this strategy. Okay, actually, I'll draw them the same shape as they are in the figure so we don't get confused. I think I would opt for this strategy simply because it is not quite as many um, formulas going on at once. Okay, so let's try the idea of adding these two triangles together. Okay, I'm going to transfer the information from the diagram. We have a 5 right there and a 13 on this hypotenuse. We have a 12 across the horizontal side of this big triangle up top. And if we look at the idea over here, this overall length is 11. 5 of it is used up right there. So how much extra length is available? There are 6 units on the altitude of that triangle. So it actually looks like we're in pretty good shape as far as making this the sum of two triangles work. Now, we do have two triangles, so our formulas are 1/2 times base times height, which will be need to add to another 1/2 times base times height. Okay, so let's see what we can plug in here. On the left-hand triangle, 1/2, remember base and height are perpendicular to each other. Well, we have the 5, okay, but we are missing the other side length that is perpendicular. We'll come back to that in a moment. On the right-hand triangle, we have 1/2 times base times height. Those are the two guys that are perpendicular to each other, and we do, in fact, have both of those. Okay, so let's step aside here for a second and see if we can find out what's going on with the other side length on the left. Okay, now on this triangle, as you can see, we have one leg of the triangle. The other leg is missing, and we do have the hypotenuse. Sounds like a perfect opportunity for Pythagorean theorem. We have 5 squared. We have an unknown length on one of the legs squared, and that should equal the hypotenuse squared. Okay. Now, this is actually one of the Pythagorean triples, so hopefully you are learning that x is going to be a 12. This is a 5, 12, 13 Pythagorean triple, but work it out if you don't. Okay. There is the side length of 12, and that was the missing side length that was preventing us from being able to work the problem. Now we should be in the clear, and let's figure it out. Okay, of course, order of operations is going to make us put all the multiplication together on the left and all the multiplication together on the right before the addition in the middle happens. Now on the left, 5 times 12 is 60, and half of that is 30. On the right, 6 times 12 is 72, and half of that is 36. If we take 30 and 36 and add them up, we have 66, and we had no measurements, so they are simply square units. Could we have gone about it the way on the left side of the page with the square or the rectangle minus the 3 triangles? Sure, we could have, but I am always going to opt for 2 formulas rather than 4 formulas, simply because it's less opportunity for us to make mistakes. All right. Like I said, as you can imagine, the diagrams can get as complicated as the person drawing them wants them to get. Okay, so let's take a look at what may be going on here. Now, different ways of thinking about this one. We can put it together as shapes being added together, and actually there's a couple of different ways that I can see as far as adding them together. Okay, press pause if you need to copy down this diagram because I'm about to start drawing on it. Okay, now one of the ways we could look at it is if we subdivided it like this, then what I see is on the left side there is a triangle, which would add together to a rectangle across the top, which would add together to a triangle on the right. Okay, so that's one way of doing it. Another way that I can see as far as the sum of shapes is possible. Maybe we could divide it across there, in which case you would have a triangle plus a trapezoid up top plus another triangle on the lower right. However, I'm not going to use either of these methods because I see a different way to look at it where it's just two formulas rather than three. Okay, and I'm going to use a subtraction. Okay, what I see is I see a regular hexagon that is missing a rectangle of some kind. Okay, so I'm going to move the information that we have here. Okay, I've got a side length of 6 there. Okay, with the one tick mark that is marked on the rectangle, I see that. Okay. We are going to have to come up with the other side of the rectangle here in just a moment. First, let's get our formulas in place. A regular hexagon is 1/2 times the apothem times the perimeter. And the rectangle that we have in there is, of course, base times height. Okay, so let's take a look at what's missing from the formulas. Okay, we have 1/2. The apothem of the regular polygon, regular hexagon, could be drawn in a lot of different places. Just going to try it right here. There's the apothem. Okay. I'm going to go ahead and put in a radius also. Okay. Now, if you remember, one of the properties of a regular hexagon is that it breaks down into 6 regular triangles, which means all of the radii inside of the triangle are 6. Now, with a side length of 6, the altitude, or the apothem, breaks the side length, that missing side length of the regular hexagon, into 2 pieces. So if we pull that little triangle out of there, where the apothem is, okay, we sure would like to know what the apothem measures. Now, if you'll remember correctly, this is a 30, 60, 90 right triangle, and we do have a rule for the 30, 60, 90 that says the long leg equals whatever the short leg is times the square root of 3. If that's the case, then the long leg equals 3 times the square root of 3. That's our measurement right there. Now, if you could not catch that or couldn't remember the rule, that's fine. You can always run it through Pythagorean theorem and see what the missing apothem would be. Okay, but we have the apothem, 3 root 3, either from the 30, 60, 90 rule or from Pythagorean theorem, either way, and we have a perimeter of 36. Now we get the 36 by saying it's 6 units on each of the sides of the regular hexagon, and there are, of course, 6 sides in a hexagon. 6 times 6 is 36. Now, on to the rectangle. Now, as far as the rectangle is concerned, we have one of the measurements, okay, it's 6. And we actually now have the other measurement, okay, because the apothem is the same length or height, either way you want to say it, as the side length of the rectangle. Okay, so this 3 root 3 that we discovered here a moment ago is also one of the side lengths of the rectangle. Okay, so let's see what we have going on there in this problem. Now we have some radicals. That's going to cause some decimal points, so that's okay. We'll allow our calculators to help us out on the decimal points, but we will not round off until we get to the end of the problem. Okay. Now on the left side there, we have whole numbers of 36 times 3. Half of that is 54. And 54 times the square root of 3 is in the ballpark of 93.53. Okay. From that, over on the right, we have whole numbers of 6 and 3. 6 times 3 is 18, and 18 times the square root of 3 is about 31.18. And if we subtract those two values from each other, 93.53 minus 31.18, then we get an area of approximately 62.35 square units. Now, they're not all that complicated. It just depends on the shape. Some shapes are prone to keeping everything as whole numbers, and some shapes, like regular polygons, are more apt to end up with decimal points and radicals and stuff like that. And of course, remember that circles are also a possibility with composite shapes, so you might end up with some pies and stuff like that in your answers. Now that's the last of the examples that I'm going to work for you. I would like you to take a little bit of an easier example like this one, copy it down, and work it out. Let's see what kind of an answer we can come up to. And guys, when I say that I want you to work it out in your notes, that does not mean show up at class and try to scramble and get something written down on this example while I am walking around looking at the notes. Get it done, bring it in, already completed. It is part of your notes, and your notes are things to be done at home, not in class at the last moment trying to fool me into thinking that you've actually done your example. Okay, I appreciate you finding time to get your notes taken care of. As I said, this is the last of the notes that'll be going towards the next test, so please pay close attention. This is obviously the hardest math that we've got, so make sure you're getting it done correctly.